We're beginning Chapter 3, and we're going to be giving you the key ingredients for inferential statistics. So it's an important concept, and I know all of you will be able to get this. So this is the first lecture about z-scores. So in our last class, just to have a little refresher, or last week's work, we worked with measures of central tendency. And we talked in specific about calculating the mean, which we represented by the letter M, and which we understood was the formula, the sum of all the scores divided by N. And we had some little terms that were used. M equals mean. The sigma sign equals sum, x equals score, and n equals the number in the sample, the number of individuals. And we also talked about spread, and so this was central tendency, and then we talked about spread. How far apart the points are from the mean, and we talked about it in terms of standard deviation, which we abbreviated at this time as SD, and we talked about the formula being a kind of a complex formula that we broke into steps. The formula for standard deviation in this model is we're going to take the square root of the sum of all the deviations squared divided by n. So that's the whole formula, but we also said that in this class we're always going to be breaking it apart. We're always going to have 3 steps. The first step is we're going to solve for the sum of squares, which is just the sum of x minus m squared. And up here, we'll note that SS is the sum of squared. We'll just write the sum of squares, or also the sum of squared deviations. And a deviation is just x minus m. Any particular score minus the mean is the deviation. And so here we have just taken the sum of all the squared deviations, called the sum of squares. The second thing we'll always be doing when solving these problems is to solve for the variance. And the variance is just equal to the sum of squares divided by n. We've already defined n, and we've already defined sum of squares. So variance, VAR, means variance, and it is used in your book, and more commonly in mathematics they write it like this, SD squared. In our class I'm always going to write it as variance because I find this to be a little confusing. A lot of students think they need to square something. It's just a little bit confusing when you're first learning statistics. The third step that we're going to take in calculating standard deviation is to do the square root, this part of the formula, and we're going to take the standard deviation is the square root of the variance. And so SD equals standard deviation. So that is the content of where we were last week. That is the most important part. So this week we're going to learn a little bit about standardizing scores. So to begin to work with our concept, let's ask each of you to think about whether you are a morning person or a night owl. And by that we just mean, do you feel better trying to get work done as you would in this upper image in which this woman seems to be really alert. She's working at night. We can see the stars, but it seems like she's pretty content and happy and feeling good. She feels good, alert, engaged at night, as opposed to this woman in the second picture who tends to feel really good, engaged, alert first thing in the morning when she just wakes up. So which one of these is more like you? And to be specific, this question asks, how much of a morning person are you? So we're looking at how much you are like this woman on the bottom. And you can rate yourself on an 8-point scale. You can see we have 8 options, 1, 2, 3, 4, 5, 6, 7, 8. So it is an 8-point scale. And if you choose 0, you're not at all a morning person. You're more like this top one. If you choose 7, you're more like her. You're completely a morning person. You're just like her. And wherever you put yourself in between represents where you think you are on this continuum. And in our example that we'll be using in our class today, we'll be having 2 students. One is Jerome, who indicated that he thinks he's about a 5, so sort of a morning person, but not quite as much as she is. And we have another person who, I believe, her name is Katiana. And she is not much of a morning person. She is way more like this top individual. So here are our 2 individuals, Jerome and Katiana, with their responses of 5 and 2 on this 8-point scale. And so what we want to know is how different are Jerome and Katiana's responses from those of typical students. So if we don't know anything about typical students or about the other students, we can't answer this question at all. However, if we have information, and in this case we do, we have data from a large sample of students in the US and Canada, and some people calculated out, the researchers calculated out the mean, which was 3.5, and the standard deviation, which was 1.5. So we have something to go on to compare Jerome and Katiana to a larger group. What does this tell us? So here again is the mean and standard deviation from the previous slide, and we can place these scores on a scale by adding or subtracting the standard deviation from the mean. So under this bar marked mean, let's write the 3.5. And now we know that each one of these units, each one of these standard deviations is worth 1.5. So let's add the 1.5 here, plus 1.5, and we find that we get a score of 5. We know that this is 1.5. And so if we add the 1.5, we get 6.5. We know that this distance is 1.5. But because it's a scale, we're going downward now, so we subtract the 1.5, and we find out that this score is 2.0. And here we have another 1.5, and we find that if we subtract it from the 2.0, we get 0.5. And so on this 8-point scale, ranging from 0 to 7, we have each of these scores linked with a standard deviation. A score of 3.5 is right at the mean. A score of 5.0 is 1 standard deviation above the mean. A score of 6.5 is 2 standard deviations above the mean, 1, 2. A score of 2.0 is 1 standard deviation below the mean, and a score of 0.5 is 2 standard deviations below the mean. So we know something. So now we can add Jerome's score and Katiana's score to the scale. Since Jerome is our first person, I've given him the name x1 with this little subtext. So the x just means score, and the 1 just means for the first person. The score for the first person is 5. So let's mark his score here. with a little flag. And here is X1. Let's mark Katyana's score. She's X2. She's the score for the second person. I'll go this way since we're now on the negative side of the distribution, or the scores that are below the mean. And here is X2, Katyana. So we can say this. We can say Jerome's score is 1 standard deviation above the mean. And we can say Katyana's score is 1 standard deviation below the mean. So we have some good information at this juncture. But we run into some problems. So to understand the problems, let's imagine now that another researcher was interested in the same construct and gathered a ton of data from thousands of students all over the country. And the only difference between what this researcher did and what the other researcher did is that this researcher used a 10-point scale, asked to rate your responses from 1 to 10. So we have a 10-point scale. And in this case, we're going to have somebody named Franklin, who indicated an 8, that they were pretty close to this person here. And we have a person named Cleo, who indicated a 3, more like this person here. So here again, we have some different scores. So here's our example then, all laid out. We had 2 responses on the 10-point scale, Franklin and Cleo. On the new scale, the researchers found that the mean is 6 and the standard deviation is 2. So how do these students compare with others, including Jerome and Katyana? This leaves us with a problem. How do we compare scores on this 10-point scale with our earlier scores that were on an 8-point scale, ranging from 0 to 7? To answer this question, we have to do something called standardizing the scales. So what do we mean by standardization? To answer this question, I want to go back to some work that a colleague of mine in North Dakota did. He went to all these remote communities of indigenous peoples who were living in Malaysia, and they were remote and kind of isolated on islands. And he was a music professor, and he was interested in their musical instruments. And he found that on each region, they had different scales. So you can see these different flutes, and let's imagine that this first flute was typical on one island, and you can see the spacing of these holes is going to lead to what pitches the flute produces. And this next one, different holes, different pitches. This next one, more different holes and different pitches. And likewise here, different holes, different pitches. Musicians from these regions didn't have any standard. All the pitches that they were using in their music were unique. And so once they finally got together, they couldn't really play music because they didn't have standard pitches. The sounds would clash with each other. And so they created a common standard. And if you've had any music here, or if you've even played a guitar or anything like that, you know that we have standard pitches that we use in music. So the thickness of the strings on the guitar are standardized. If you buy one guitar or a different guitar, the thickness of the strings will be the same, so that depending on how much you tighten them, you're going to be able to find the right pitches to play with other musicians. So you can see the benefit of a standard. Some more examples of standards are our ways of measuring, say, length or time. We measure in minutes, and we measure it the same way. Like the length of a minute is consistent wherever you go. It's a standard. Or volume, quarts and ounces. We have measurements on this, and if you buy, a 12-ounce can of pop, it'll be the same volume. An ounce is an ounce is an ounce. The same with pounds. as a measure of weight, or kilograms if you're using the Celsius scales, the centigrade scales. And so a standard is just an accepted or approved instance or example of a quantity or quality against which others are judged or measured or compared. So we have a standard now for weight, and this saves us some trouble. Because imagine being in one of these markets and you want to buy some fruits or vegetables and we don't have any standards. And so the seller, the vendor, just says, well, I'll sell you a bag full for $1.99, and you might be wondering, how much is a bag full? Bagful is not a standardized measurement, and the weights on the scale in this top image may be standardized for that area. Maybe these weights are standardized, but we don't know. And so we have standard ways to measure things that help us improve communication, help us live with each other, and buy and sell products. So we talk about units of measurement when we are working with measuring anything, and all it refers to is the individual units that make up one when we state a dimension. So if you imagine that we want to measure this length of rope for some reason, we have a few different ways we could do it. So let's say you don't have anything with you could measure it with. Well, you could measure it with your thumb. You could, measure one thumb up against the other, thumb, and count how many thumb widths you can get till you get to the other end of the rope. And in that case, thumb width would be the unit of measurement. It would be unstandardized, however, because everyone's thumb width would be different. And so we couldn't count on this as a standard unit of measurement. We could also forget about the thumbs. Maybe we found a paper clip, and we could measure it as the length, the number of paper clips that fit. And so in that case, the paper clip would be the unit of measurement, but it would still be unstandardized because paper clips come in different sizes too. And the more common way that we use is we use inches or centimeters. And inches is the standardized unit of measurement in the United States, and centimeters is the standardized unit of measurement in other countries. And with that, we could sort of line up, like if someone measures whatever it is that you're interested in centimeters, you could easily look up and find out how many inches. So 2 inches is approximately equal to 4.5 centimeters. And in this loose example, it's approximately equal to 2 paper clips. And we've already removed our thumbs, so we can't comment on that. One way to standardize data in statistics is to use a scale called the Z distribution. And that's what we'll be working with today, the Z distribution. It has these certain characteristics. First, it follows a normal curve, and you remember the normal curve, that one that's symmetrical, bell-shaped, and unimodal. Secondly, the mean is always 0. So always the mean is 0, and always the standard deviation is 1. Very easy to remember. And the tails extend to infinity. So we'll look at this more closely on another slide. And we can also say that any type of scale that follows a normal curve can be transformed into z-scores. And z-scores allow us to understand the distribution regardless of the original scaling. So the answer to the problem is standardizing raw scores with z-scores. So just a reminder, some definitions, that raw scores are the scores for each individual on a specific scale, and we indicate them as X. So like Jerome's score of 5 is an example of a raw score, and z-scores are scores on the standardized scale indicated as Z. So just like we align centimeters with inches to compare lengths on these two scales, 1 inch is approximately equal to 2.1 something centimeters. We can do the same thing with aligning raw scores with z-scores to compare spread on different scales. So this is the Z distribution. You've already seen it. The mean of 0 is indicated with a dark bar, and we can see the standard deviations. Here is 1 unit. Here's another unit. Here's a unit. Here's a unit. Each standard deviation is 1, going in positive numbers to the right and in negative numbers to the left. So when we align it to figure out, to change, to transform raw scores into z-scores, we just line it up this way. So here's our 3.5. We've already done this. We know the standard deviation is 1.5. So here we have our 5.0. 1.5 is this distance on the unstandardized scale. So when we add the 1.5, we get 6.5. The units to the left of the mean are also worth 1.5, so we take them away to get 2.0, 3.5 minus 1.5, and we take them away to get 0.5. And so if we line these up, for example, we can put Jerome's score on as we have done before, and here is his score of 5.0. And if we line it up, we can see that x1 equals 5.0 and z1 equals 1. And that's how we can align these up to find out what they mean. But even more than that, our scores allow us to compare scores on different scales, just like we did comparing inches to centimeters. Now we can compare our 8-point scale, which we did on the previous slide, to a 10-point scale. I'm going to pull up a different color here. So here is our 10-point scale that we used for Franklin and Ch03Aau. So 8-point scale and 10-point scale. We know that the mean of that distribution was 6. And we know that the standard deviation was 2. Let me write this here. The mean equals 6. The standard deviation equals 2. So here are our 2 units. 6 plus 2 is 8. Here are our 2 units. 8 plus 2 is 10. Our 2 units, 6 minus 2 is 4. And again, 4 minus 2 is 2. So now, to find out, let's say Franklin's score, we know that Franklin was x3, and his score was 8 on the 10-point scale. And we can simply draw a line, and we can see that just as Jerome's score, z-score, was equal to 1, Franklin's z-score is also equal to 1. So x3 equals 8, z3 equals 1, and I'm just putting the 3 there because Franklin was our third person. So from just doing this comparison, we can conclude, let me put in Jerome's score here. Jerome's score was also right here. It was 5.0, also right here. And so we can conclude that even though Franklin had x equals 8 on a 10-point scale, Jerome x equals 5 on a 7-point scale. We know on an 8-point scale, we know that the score for Franklin, x3, is equal to the score for Jerome. So we know that z3, Franklin's z-score, is the same as z1, Jerome's z-score, and that both of them equal 1. So there's no difference, even though it looks like Franklin had a higher score than Jerome. We can also plot on here our score for our last person, Ch03Aau. We know that Ch03Aau had a score, she was our candidate x4, and her raw score was 3 on the 10-point scale. So the 3 on the 10-point scale falls right between the 2 and the 4. There's where the 3 is. So we can draw the line right here, straight up, and we can find that x4 is right here, and the score right in the middle of -1 and -2 would be -1.5. So we know then that Z4 equals negative 1.5. X4, of course, equaled 3. So this allows us to compare scores on different scales using a common language. So we'll go through and do some more examples. So we also know then that the z-score can be represented on the normal curve, and this is our standard normal distribution. And what we're going to do at this point is just work with another simple distribution. So let's work with a distribution and let's call it a fitness test. That's the data that we'll work with. And I'm going to go ahead and put the z-scores on here so that we're very clear. So the center is always the mean, so our z distribution will be in this dark blue color. The mean is always, as you've learned, 0, and each standard deviation is worth 1. So we have 1 standard deviation, 2, 3. Going the other direction, we have -1, -2, and -3. And these are the scores for our z distribution. Now, going on to our fitness test, let's elect to use a different color here. I think we'll use the green color for our fitness test, so I'll put a green little line under this. And this test has a mean equal to 50 and a standard deviation equal to 10. So we can write these scores. I'll put the X here to show we're writing these scores. We'll put the mean in the middle, and now we'll add the tens. So I'm going to write them up here. Each distance like this is worth 10. So 50 plus 10 is 60. This one is worth 10. 60 plus 10 is 70. This one is worth 10. We come to 80. We can do the same on the area below the mean. 50 minus 10 is 40. 40 minus 10 is 30. And 30 minus 10 is 20. So there is the distribution that we're going to be working with. So now let's have a few individuals provide scores. So our first individual is Jose, and he had a raw score. This is our first individual. I'll name him 1. So score 1 equals 60. Z equals what? So here we just find our raw score 60, and we can put in our flag following it right up. Here is our score for Jose. We'll call it X1, and we can see that it is perfectly lined up with the 1 on the z distribution, so z equals 1. Our second individual, Kendra, she's our second individual, so I'll call her X2, equals 30. Z equals, we'll leave a blank. Let's mark her score. Here's the 30. I'll follow it up here. I tend to put the flags in the opposite direction when we're working in the scores below 0. So there's X2. And if we line it up, we can see that it's perfectly lined up with a z-score of -2. And let's do one more. Marion, X3 equals 50, Z equals blank. And so let's mark Marion's score. And here is the 50, so her score is right in the center. So let's get this marked as X3. And we can see that it's lined up with the z-score of 0, which makes sense because the mean of the raw score distribution is the same as the z-score of 0. Let's do one more person who doesn't fall exactly on the mean. Let's do Olivia, X4, and she has a score of 75. And we want to find out her z-score. And so where does the 75 fall? Well, we know that it falls midway between the 70 and the 80. So the 75 would fall right here. So let's draw the line straight up and mark Olivia's score, X4. And we can see that it falls exactly halfway between the 2 and the 3. So the score must be 2.5, which is what would fall right between the 2 and the 3. And so that's how we can go from the X scores to the Z scores. We can, of course, do the same in reverse. So let's quickly set up the distribution in the same way. Here is the Z distribution. We have 0, 1, 2, 3, -1, -2, -3. And let's set up our fitness test distribution, which has a mean of 50 and a standard deviation of 10. Here's 60. Here's 70. Here's 80. Here is 40. We subtract 10 to get 30, and we subtract 10 to get 20. There is our X distribution for the fitness test. So there's our fitness test. The mean is 50, and the standard deviation is 10. What if we don't know X scores? We instead know Z scores. So let's imagine some individuals. Do a couple of these. Let's imagine that Sandra, our first person, has a Z score. The Z score for the first person is equal to -1. Well, we can use the same thing to discover X in her case. And so if we have a -1 as the Z score, we can draw the line up, mark it, here's X1, and we can see that the score that corresponds with it is 40. If we have Terrence with a Z score equal to 1.5, and we want to know his raw score, we can find where 1.5 would be, and it would be, of course, midway between the 1 and the 2 is where we'd have 1.5. We can go upwards to draw in where Terrence's score would be. And so we have Z2. And if we draw this line going downward, we know that it's going to be the number midway between 60 and 70 would be 65. And so we know that his score is going to be 65. So sometimes we find that we have scores that don't fall right on these lines or right between them, so it's a little harder to estimate what they might be. So we also have a formula that we can use. So let's imagine that we have Samantha, Sam, with a raw score, X, here's our first person, so we'll give it X1, equals 68. Now, what is her Z score? We can estimate it by plotting where the 68 would be. The 68 would be right around here, right? Closer to the 70, but between the 60 and the 70, which would make it, if we draw a line straight up, fall next to a Z score somewhere between the 1 and 2, but closer to the 2. So in this case, we can approximate the Z score, and if we are even pretty good at, extrapolating information because we're working with multiples of 10, we can probably figure out that it's going to be about 1.8. But let's do a formula to check our work. So if we have a raw score and we want to know a Z score, we can use a formula, and that formula is Z equals X minus M. You probably recognize that as the deviation, but we're going to take and divide by the standard deviation. And so in this case, we would have Sam's score 68 minus the mean, which is 50, divided by the standard deviation, which is 10, which equals 18 divided by 10, which equals 1.8. And that is right about, that's what we predicted, and that's right about where it looks to be between this 1 and the 2, so the z equals 1.8. For another example, let's take another individual. Yolanda, and her score equals 41. And once again, we could extrapolate what her score might be. So we know the 41 is going to be really close to this 40. And we know that the line we draw upward is going to be about like this. And we might even be able to estimate that it's going to be 0.9, a number between 0 and -1. So negative 0.9 is my prediction. But let's check it with math. So we know the formula. Let's just write that formula down again. Z equals x minus m divided by SD, which equals 41 minus 50 divided by 10, which equals -9 divided by 10, which equals -0.9. That looks like what we predicted. Let's not forget the negative sign, and that's exactly where it would appear to be. So we have Z2 equals -0.9. Similarly, we can go from Z to X using a formula. So imagining that we have an individual, Zoe. She's our first individual, and we know her z-score. So Z1 equals 2.16, and we want to know what x1 equals. So we know the z-score of 2.16 will be somewhere in this neighborhood. So there's our z1. And we know it's going to be, if we trace the line down, it's going to be something between 70 and 80, a little bit closer to 70. And so let's look at the formula for calculating it. So to calculate the z-score, when you have x, you use the formula, x, not z. See if I can erase on here. There we go. X equals z times standard deviation plus the mean. It's just the reverse of the formula we just used. And that would equal, in this case, 2.16 times 10 plus 50. And 2.16 times 10 equals 21.6 plus 50 equals 71.6. That works out beautifully with what we just predicted, so we can put 71.6 as our response to that item. Let's do one more with this formula. Let's use an individual, Andrew. Our second person, Andrew, had a z-score equal to -0.62. And we want to know what the raw score equals. We know we can plot it. -0.62 is going to be somewhere between 0 and -1. And it's going to be a tiny bit closer to the 1, but it's going to be somewhere like this. And we can draw the line upward to mark him. And we can continue the line downward to predict that his score will be somewhere between 40 and 50. In fact, probably between 40 and 45 and closer to 45. But let's go ahead and do the math and calculate it. So we know the formula for x equals z times standard deviation plus m equals negative 0.62 times 10 plus 50 equals negative 6.2 plus 50, and that equals negative 33.8, squeezed in at the bottom there, and negative 43.8. Sorry about that calculation problem. Negative 43.8 falls just where we predicted, and so 43.8 is his raw score. So to conclude, we can say that the Z distribution is a standardized distribution representing normally distributed large data sets. The Z distribution always has a mean of 0, a standard deviation of 1, and tails that extend to infinity. X refers to raw scores, or scores produced by individuals, and the distribution that represents them. We can estimate Z and X scores by aligning them along the standard deviation lines. And we can calculate Z if we know X using the formula Z equals X minus M divided by standard deviation. We can calculate X if we know Z using the formula X equals Z times standard deviation plus M.